This video is going to demonstrate one of the critical principles of sampling, and that is the idea of a representative sample or a biased sample. Biased samples would be bad. Representative samples is always the goal. And in this spreadsheet, I have a graph set up to create a histogram of whatever data we collect. And up here we have a formula that calculates the sample mean automatically. And here we have a formula that calculates the sample size. And I'll increase the number of data points that we collect, and you'll see that this updates automatically. The stuff over here and behind the graph is a bunch of technical formulas that are going to calculate the number of data points in every class. And we'll use that to graph the histogram. If you see here, I think, there we go. So the values that are going to be calculated in the histogram are going to be these columns here that are calculated in the background. Now over here, we've got values that are going to represent heights. So right here we've got the height of a randomly selected person. This is a number that we're just going to ignore for now. It's a random number between 0 and 1. And this here is going to be the gender of the person, and presumably the males are going to be on average taller than the females. And right now we're just randomly selecting one person, and if I copy these formulas down, and we'll see over here, now we've got 13 people. That's our sample size. And of the 13 randomly selected people we have, here are their heights. We have a sample mean, or an average height, of about 67.8 inches. And down here we've got a histogram, and we can see that it's kind of bell curved. For this sample it appears to be a little bit left skewed, meaning there's a tail to the left. And that means something about the mean versus the median, and there's all sorts of other things we could talk about if we wanted to. Now, in the process of sampling and making inferences about our population, the process of inferential statistics that we're just starting, when we get a sample of data, we've got 13 values here, and for illustration's sake, I'm going to stretch that out a little bit further. So now we've got 24 different data points, randomly selected males and females, and then I've got a function built into Excel that creates heights for them. If we look at this sample mean of 67.5 or so, 67.5 inches, that's the mean of the 24 observations that we looked at, or our sample mean. What we hope to do is to use that sample mean of 67.5 to make an inference about the mean height of all people in our population from which our 24 people were randomly selected. Now, if I had to guess a single number, I would say that because our sample mean was 67.5 inches, that was the mean of the 24 people that we looked at, I would guess that the mean of all people in the population is also probably right around 67.5 inches. However, if we randomly select 24 more people, now we get an average of 66.8. And with this sample, if I had to guess a mean for all people, the population, now I would guess that the mean is probably 66.8. Now, it's possible that the true mean is 66.8. It's possible that the true mean is 67. It's possible that the true mean is 70. We would probably create something like a confidence interval, which is done in the next chapter, like a range of plausible values. Before we do any of that analysis, though, we have to justify that our sample, and therefore our sample mean, our sample of 24 people that created a mean of 66.8, to justify that the population mean is probably somewhere around 66.8, you have to try to provide some sort of reason to believe that the 24 people that we looked at is representative of the population. That is, they're randomly selected. Now, this is a complicated formula that I use to create the heights. And essentially what it says is, if the gender found in cell C2 is F for female, then we're going to randomly create a height from a normal distribution with an average of 64 inches and a standard deviation of 2.2. That is, females on average are 64 inches tall, and 68% of the time they're between 61.8 and 66.2. That's the empirical rule. If the value in cell C2 is not an F, meaning the person is a male, then Excel randomly generates a height for males with an average of 70 inches and a standard deviation of 2.2. And those numbers are not researched at all, I just made them up. Well, that kind of explains why in our histogram here we sort of have two different peaks. And maybe I'll generate 24 more values, and 24 more, or 24 more. That's a nice picture. So the reason that we have kind of two different modes or two different peaks to our little bell curves here is that most of the people down here are probably going to be females who have an average height of about 64 inches. And we didn't get anybody that was 64, but we got a lot of people that were in the 65 range. Most of these are probably females, and most of the people over in this range are probably males who have an average height of about 70 inches. Now, by design, because the average height of females is 64 and the average height of males is 70, I would expect that the population mean is probably right in between 64 and 70. That would be 67 inches. And you watch our sample means up here. We've got 24 observations, we got an average of 68. If the true value is 67, we kind of over-predicted that, but sometimes that happens. Here's 24 more observations, and now we have an average of 67.5, 67.8, 66.7. You see, sometimes our sample mean is above 67, sometimes it's below it. Now, if I take these formulas and I stretch them down a long, long way, maybe down to, I don't know, 1,500 values maybe. All right, a little more than that. Go way back up to the top. So now we've got a sample of 1,512 observations. And in theory, the population mean should be exactly 67, half males, half females. Now, if you're a believer that because of the way chromosomes and genetics works, that the population should actually have about 51% females and 49% males, which I think is the case, then you'd expect that this average would be just the slightest bit below 67 inches. And when we're looking at 1,512 observations at a time, a very, very large sample size, you would expect that this histogram would look exactly like the population. And this sample mean here should be really, really close to the true population mean. Why is it then that this sample mean is not 67 inches, or maybe slightly below it? Well, maybe that was just bad luck. So we collect another sample of 1,512 observations. And again, we get a sample mean that's above 67, although it's close. Now it's 67.2, 67.2, 67.3, 67.3, 67.3, 67.3. You should start wondering why, well, that's 67.6, that's very strange. Why aren't we getting values that are occasionally below 67 to offset the ones that are above 67, which would let us believe that the true average really is 67? The problem is because this sampling process is biased. Now, I have been very careful to not show you the formula that was used to calculate these other two columns. And that's to illustrate a principle that when we go out and collect data, a random sample, a lot of times we won't even realize that our sample is biased. Suppose we go out and we just randomly survey people at, say, a shopping mall. And we say, what gender are you, and how many pillows do you sleep with at night? Now we would expect to get probably half males and half females. And maybe females use 2 pillows a night and males tend to use 3 because they have bad backs or something like that. Now that means that on average you should get a value of about 2.5. Half males, half females. Females use 2 pillows, males use 3. On average it should be 2.5. What if, without realizing it, by choosing to collect our data at a mall, we're more likely to get females than males? That means that on average, the mean of our sample is not going to be 2.5. It might be something like 2.3 because we're getting much more females in our sample than males. That's what's happening here. You see that in this histogram, the peak of what should be the female area, this area right around 64 inches or so, is a little bit shorter than the peak around 70 inches, which is the average of the males. The way that this column here, column C, is generated, I'm not going to show you the formula, but it causes our sample to include 55% males and only 45% females. Males on average are 70 inches, females on average are 64 inches, and because we don't get a 50-50 split, if we're trying to study the average of all people, our sample by design is more likely to catch males than females, and so it's more likely to overestimate the true population mean height of all people. And there's a very famous case of something like this that happened in politics and political polling. And you can look it up. There's, I think, a Wikipedia article just for this one particular case. And there's probably lots of examples in statistics references and statistics textbooks and things like that. In the presidential election for Harry Truman, right around the end of World War II, he was running against, his name was Dewey, D-E-W-E-Y. President Truman is T-R-U-M-A-N, if you want to look him up. And in this poll, lots of reputable agencies were talking to people by phone, calling them up, and asking ahead of time, when the election comes around, do you plan on voting for Harry Truman, the incumbent, or do you plan on voting for Dewey? The polls were indicating that Dewey was going to win in a landslide. In fact, pollsters were so confident of this that newspapers began publishing newspapers that said, Dewey wins, Dewey's our next president, before the election even finished. When the results of the election came out, it turned out that Truman actually won. Now, the reason that the polls were so wrong wasn't because people were collecting data in a wrong way, or people were lying about the data, or the people who were participating in the poll, that is the sample, were lying about their intentions of actually voting for Truman. The problem is that the poll was collected by calling people on the telephone, and it just so happened, without even realizing it, that the people who were collecting the data were more likely to be talking to people who supported Dewey. Because back in the 1940s, not everybody owned a phone. In fact, only the wealthier people owned phones, or maybe were more likely to answer their phones. And those people who owned phones and were probably wealthier were more likely to support Dewey. So by collecting your data in this way through phone calls, you were biasing your sample, or the polls were being biased in favor of Dewey supporters, and that's why the true results of the election that Truman won were different than what the poll was saying. And it's because the polls, or the sample who was trying to collect data from these either Truman or Dewey supporters, were biased and more likely to collect certain people in the population that was Dewey supporters than other people in the population that would be Truman supporters. Exactly that same process is happening here. There's nothing wrong with the way that these heights are being generated. The males on average are 70 inches tall, the females are on average 64 inches tall. And you wouldn't notice anything just by looking at the data. We've got a bunch of males, a bunch of females, and it's about half and half. Without even realizing it, the way that this data was collected is more likely to choose males than females. The same thing could happen in any other study. You could be collecting information on sales of a particular product, that is, how many of a certain thing do you buy. whether or not you prefer nacho Doritos to spicy nacho or spicy cheese or Cool Ranch Doritos or something like that. If you go collect your data by talking to college students, you may not even realize that there's a problem, but perhaps college students tend to prefer Cool Ranch Doritos more than any other type of person. So by collecting your sample by only talking to college students, you're going to get a disproportionate number of Cool Ranch prefers and not enough people who prefer the other types of chips. Now, the only solution to biased or unbiased sampling is to just use your intuition. If you want to go collect data at a shopping mall, there may not be a problem, but you have to ask yourself, by only talking to people who would go to a shopping mall, are you more likely to get people who have one sort of behavior or certain preferences relative to other people? As a really obvious example, suppose you want to measure the height of all people. Does it seem appropriate to go to a basketball game and then start randomly asking people what their heights are? I think you'll realize that if that's your method of collecting your sample, you're likely to get a measure of heights and therefore an average level of heights that is not representative of the true population.